Welcome back, everybody. I'm Danny, and this is the Stock Car Surplus YouTube channel. Today, we're going to go over suspension components, namely front suspension components. I've been away from doing videos lately. I've been pretty busy, and I've had time to do this, but I've had time in the evening to get our Camry COT rolling. One of the things that hasn't stopped is a number of questions that continue to come in asking, how do I measure my spindles? What do I need? Where do I find road course components? And a lot of the questions also concern the numbers people find stamped on parts and pieces. Everything from upper control arms to stuff that's stamped on a spindle. We're going to talk about that, and we're going to go into actually measuring them. One of the questions I get is, hey, what kind of spindle do I have? And without being able to measure it, you're never going to know what you need to match it up. There's a big misconception out there that you need a certain road course spindle to make your car turn left and right. That's a big misleading factor. Road course spindles depend on your type of driving and what you want out of your car and how you want it to handle. I don't care what anybody tells you out there, every single car is different. If you find someone on the internet telling you need to put this degree of caster in your car or this degree of camber and your car is going to run straight and you can road course it even though it's a left turn car with a wrong cambered rear and house and you can take it to Road Atlanta, they're full of crap. Don't believe it. I'm going to show you how to measure this stuff. We're going to break out some jigs and we're going to do some breakdown on that. And we're going to start with spindles. I've got a spindle jig here. I've made several sets of spindles off of this thing. I bought it from a friend who recently passed away a couple years ago. Same thing goes for this upper control arm jig. Now the lower jig is a big table all into itself and it's sitting over there off camera. We're going to talk about lower control arms as well. But first we're going to go into this jig and we're going to talk about the different types of front spindles and what you need to make your car turn left and right. Let's jump into this. The first thing we're going to talk about are the two main components of a spindle, the spindle upright and the steering arm. Now, if you're standing in front of the car looking at it and the engine's in front of you, this is going to be your right steering arm and this is going to be your left. These are the two major components. When it comes to this upright, it's universal. It hasn't been determined whether or not this is a left or a right spindle upright. That's not determined until it's machined and a steering arm is mounted to it. This could be a left, this could be a right. This is an unfinished blank, which means it only has the big bearing 2 9/16 spindle pin machined on it. This entire thing is forged. Now, this could be an 8 degree, this could be a 10 degree, this could be a 9 degree, it could be a 5. It just depends on where in the top of the spindle that the ball joint hole is mounted. The height can also be adjusted. This can be adjusted all the way down to a very short spindle or a standard 10-inch spindle. It depends on who is building it and what it's used for. On the back of the spindle, you can see this flat area here that's been machined into it. It's got that small curvature in it so that it keeps the center OD and pin alignment for the inclination measurement. Now, here's our steering arm. For this spindle, the steering arm would be machined and bolt on here. Now, this could be a standard drop spindle. You can move it down further for a deeper drop. This can be up to a 2-inch drop spindle blank. That's what this is, nothing more than a blank that's unmachined. Now, if you look at it from the front, let me grab another spindle. This is a standard pin spindle that's been used since the mid-2000s. This is 1 3/4 inch in diameter. This is 2 9/16. About 99% of you out there will probably have this diameter spindle pin on your race car. Some of the older stuff, you'll find some diameters that are 1 9/16 inches, and you'll find some that are 1 5/8 inches, depending on the era of the car and whether it's a front steer or rear steer. We're going to stick to front steer stuff. So let's move this to the side and let's bring in another spindle. Here we have, let's make them the right way. Now, standing here in front of them and looking at them, we have a right and we have a left spindle. Now, looking at them to the naked eye, most people might think, well, the only real difference is the brake bracket. There's a whole lot going on here. These are two totally different spindles, and unless you were running a short track somewhere, these would not work for a road race application. But you can make a car go straight with them if you understand alignment and how to set up a car. Now, this spindle on the right, this spindle is actually a left side spindle. This is a standard height spindle. What does a standard height mean? Well, the overall height of this spindle, if you measure it from the actual ball joint pin to ball joint pin, is 10 inches. That is your standard height of a spindle. This one is shorter. This one is 9 1/4. On the top of this spindle, you can see right here where it says 3/4 DT. That means 3/4 drop top. That means this has been machined down. As we talked about on this spindle, this portion of the spindle would be machined down, cut the top off, and the ball joint would be mounted here, and it would shorten up the drop top of the spindle. There are some other things to look at. Not only is this a shorter spindle, but the ball joint inclination is different. On the top of this spindle, this one here says that it is an 8 degree, and on the top of this one, you can see that it is a Laughlin 11 degree. It's stamped right on the top. Many of these have the number stamped on the top or the back of the spindle shaft right here. Pretty easy to find. Now, let's talk about drop spindles. And we're talking about the bottom of the spindle. This is a standard drop spindle. What does that mean? That means from the bottom of the spindle pin to the bottom of the ball joint, we have 1.5 inches. Pretty simple to see. Now, if we flip it around with this spindle and we measure from the bottom of the ball joint mounting surface to the bottom of the bearing mounting surface, we have 2.5 inches. So this is a 1 inch drop spindle. On the top of it, 1D, 1 inch drop. What is a standard arm? Pretty simple. This is a Hopkins master arm right here. So to measure this, we're going to go from the bottom of the steering arm to the bottom of the ball joint mounting surface. Straight across here, 1.25 inches. That is your standard drop steering arm. Now if we go to this spindle here, we'll flip it up and we'll make it a little bit easier to measure. Now with this one, what we'll do is we'll take our straight edge, we'll lay it across the bottom of the tie rod mounting surface on the steering arm, and we'll measure back to the ball joint. That one is 3/4 inch. If we flip it up, you can see on the arm right here, 3/4 D, 3/4 inch drop. If you look at a lot of this stuff, you will see these numbers stamped everywhere and it will tell you. Now this arm here, this is a standard drop arm. There's nothing stamped on it. And to make sure it is a standard drop arm, what we'll do is we'll take our tape measure and our straight edge once again, and we'll measure to the bottom of the ball joint mounting surface, 1.25 inches. So we know that's a standard arm. That's how to measure some of the basic components that are on them. Now we're going to take one of these and we're going to put it into our spindle jig, and we're going to talk about spindle pin inclination and how the spindle is assembled. Now this is my spindle jig. This can build a left or a right spindle, and I've used this jig to convert many rear steer spindles with the older bolt-on Hurst Earhart bracket to a radial mount bracket and update them for vintage racing. We'll pull these brackets off and we'll set them to the side. The spacing on these brackets is 5.25 inches. If we go and we measure across here from 1 inch to 6.25, subtract the inch off the end of the tape, that's a 5.25 mounting center. That is what your typical updated bolt-on brake mount looks like, and that is the typical spacing, 5.25. What we're going to do is we're going to drop a spindle in here, and we're going to talk about how some of this stuff is actually put together and welded. Now, this spindle here was built by a race team. As you can see, it has the drop-in marks that drop all the way in, and you can weld the entire thing together. All of this drops in, goes straight through, and it holds the arm to the bottom of the spindle. Keeps everything in line, and you can weld all the way around this with a TIG welder to weld your steering arm to the steering upright. Once you do that, and those are taken apart, depending on where you get your hardware from, these are spindle bolts. These are from Spindle Joe's. They drop in, tighten them up, and you have 2 shear points. You have the bolts and the TIG weld. The spindle's not coming apart. As you can see on the back, the spindle has been reinforced. This is not uncommon. As you get into the Gen 6 era of the car, many of these spindles, teams would build them themselves, and they would CNC machine them out of a one-piece steel billet to make a spindle. Now you can see this spindle has been built by a race team, so their spacing is the same, but their distance from the outside edge of the brake caliper mount to the spindle shaft is different. So once we line this up and we put our pins back into it and we lock it in place, We can take this and turn it, and I can show you brake brackets. This is an entire tote of brake brackets right here. These are welded on to mount your caliper mount to the actual spindle. This is for a bolt-on radial mount. These come in every different size, piece, angle. They're available from several manufacturers and different people. A lot of them come from teams. They bolt on simply like this. And depending on this end, I would make a paper pattern for one of these, and I would cut one of these down because that is rounded. So this would go in something like that. I would round this off more, and I would TIG weld this entire assembly. Now, as you can see, this bolt-on bracket is longer than the whole mounting point. So what I would do is I would make a pattern of this, and then I would put this in the mill, and I would mill this out into an L shape so that it overlapped the actual upright of the spindle. What do I mean by that? We'll pull this out and I'll show you. The front of this one has been machined so that the brake caliper mounting bracket wraps around the spindle. If I was mounting this to this spindle, I would do the same thing from this side, machine it out and make it fit, TIG weld the entire thing together, and it would work like a champ. Up next, we're going to talk about spindle pin inclination. The top of this spindle says that it is an 8-degree spindle, and we're going to measure that. And what that means is the pin inclination in reference to the upper ball joint and the center line of the pin in the spindle, not the lower ball joint. It's a totally different angle. Now, if we take our straight edge and our angle finder and we stick it on here and we measure it, you can see this one comes in right at about 11 degrees. And why is that? We're only measuring from the outside edge of the ball joint mounting point to the outside edge of the lower ball joint. Now, this spacing can be different on the outside of every single one. There's no set difference to machine off here. I've seen some of these that were 1/2 inch thick. I've seen some that were 3/4 of an inch thick. And if you have an upright with a slug in it, that changed it as well. So what we're going to measure is the pin inclination from the center line of the ball joint to the center line of the spindle. Pretty simple. They make tools to do this. What we're going to do first is we're going to bolt in our spindle checking tool. Pretty simple. Just keeps it from moving. A little bit of tension on there. This is a solid stainless steel rod. This rod is machined with a tight tolerance. It slides in. What we'll do now is we'll measure this. That comes out at 8 degrees. Let's stick another spindle in here and I will show you the big difference in why you should not measure between the top and the bottom of the ball joint area of a spindle. Let's stick this left front spindle in here. This is an 11-degree spindle. This has a 1-inch drop on it. So what does that do? That moves our mounting location down 1 inch lower for the steering arm because the spindle's longer. This area has been machined out. As you can see, all of our bolt holes line up for our caliper mount, so we'll stick a bolt through the bottom here. Now, like I said, with the 8-degree spindle, you can't measure from here to get your pin inclination. That is incorrect. One of the easiest ways to show you is that we'll mount it up here on the outside of our ball joint mount and then hold it across, but it doesn't even touch. Doesn't even touch the bottom of that. That's because it's machined at 2 different angles. If we make that touch there, as you can see, there's daylight underneath the bottom edge here. And because that's open, you cannot accurately measure your spindle pin inclination. So what we'll do is we'll set this to the side. Once again, we'll grab our insert for our spindle checking tool. We'll run it in, put a little bit of tension on it, slide the rod through. We'll stop it just past the center line of the spindle pin and take our dial gauge and we will measure it. This is an 11, comes out at 79 degrees. That is 11 degrees. So the marking on top of this spindle is correct. Very simple, very easy to see. And like I said, that's how you can measure these spindles. And that's what tells you what the different numbers on them are. Now, as I said, those are your main dimensions when it comes to a spindle. Overall length, standard is 10 inch. You want to be able to measure the drop on the arm as well. The standard drop on an arm, as I said before, is 1 1/4 inches. All of these numbers are going to be stamped on a spindle. As we move around and we look at them, I'll pull these out again and we'll just talk about some of that stuff. Typically on the top of your spindle, you'll have the number stamped onto it. I'm not sure what the 130T means on this one because it's not a 13 inch. D is a 1 inch drop and then we have 11 degree on the top. Now, there's nothing saying that the spindle arm has changed. It just has a 1-inch drop, which, as I said, is going to be the difference between the bottom of the spindle pin and the bottom of the ball joint mounting surface. The same thing goes for this. As I said, this is a 3/4 drop spindle. So we'll drop it in the jig and we'll measure it once again. That one is 9 1/4. And as I said, it's got that arm on it. So when we go to measure that arm is a 3/4 inch drop. So instead of 1 1/4, it's only a 3/4 inch drop on it. And if we go to the other one, we'll pull this out. I'll grab this spindle here. This is also a left front spindle, but we'll go ahead and measure it. This one is a 10-inch standard spindle height, but this is a 1/4 inch drop arm. So we go through and we measure it. It's got a 1/4 inch spacing in it. That's the 1/4 inch drop. And once again, these numbers are just about on everything. 1/4 inch arm, and then if you start reading the top of it, 8 degree super speedway, which is probably why it has the 1/4 inch arm on it. And then it says 1/4 A, which is going to stand for that. Pretty simple on how to go about reading these. And the same thing goes, like I said before, when it comes to the ball joint, the tapers on them, one is a 727 and one is a 772. These are a Chrysler ball joint style taper. And as I said, this jig works really well for measuring spindles and welding on brake brackets. Altogether, I've done countless sets of different brake brackets welded on here. Make sure the spacing is right and all of the different weld on tabs. That's about it for spindles for now. We're gonna move all this stuff to the side and we're gonna talk about control arms. Up next, we're going to talk about upper control arms. Now, this is an upper control arm jig. I got this from a friend of mine, Mr. Danny Earnhardt, super cool dude. I bought this from him back in the day, and it came out of the 2448 shop. It's stamped on the other side. This jig I've used for countless purposes, not only to build new control arms, but to check the length and to check the actual ball joint angle on the end. This is a very good tool. And like I said, I built a ton of stuff off this jig. It's one that I'll never get rid of. It's marked all over and it's easy to read and it's easy to set up and tell you exactly what you have when it comes to a control arm. Now, there are a lot of numbers stamped on the control arms here, and I'll grab this one and we'll talk about it. Now, as you can see with this control arm, it's marked 8 3/4. That is the overall length from the center of this shaft to the center of the ball joint. This is a team number, upper control arm, blah, 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 blah. Manufacturer, hard parts come from Ronnie Hopkins. And over here, we have 1/2 inch forward, left side. So this is gonna go on the driver's side of the car, and it tells me that the ball joint is placed 1/2 of an inch forward. Now, what that 1/2 inch forward means is in relation, both pivot points, find the exact center, and you measure across, you're gonna find that this ball joint is a 1/2 inch forward. That's what that means. Now, why is it forward on this side? On stock cars that run oval track configurations, they split the caster, which means you'll have negative on one side and positive on the other side. It's a split. It helps the car cut the corner and turn through the middle. We're gonna set this to the side and we're gonna talk about the one on the jig and how to actually measure these. Now, here I have a control arm mounted into my jig, and we're gonna talk about a bunch of the numbers stamped on the jig. First, we have positive 1 inch, means on this side, if you bolt your control arm here, you add an inch. If you bolt your control arm here, you subtract an inch from your overall width, which is measured in a tape down here. And we're gonna go over that real quick and we're gonna figure that out. Now I'm gonna turn the jig this way. Now that I have our jig turned, we can talk about the control arm and what a bunch of these numbers mean. Now we have 8L on the shaft, means 8 inch left. We have 0, which by looking at the gauge here means 0 offset, so the ball joint is centered. Now I'm not sure if the S means standard for the team, and I'm not sure if that's supposed to be an N or a Z. But what I can tell you is that it is a 0 offset ball joint, and by the stamping on top of our mount here, it says -1 inch. So the front of our gauge here is right on the 9 inch number. So if we minus that inch from that, we get the 8 inch ball joint, which is what we have. Let's look at the ball joint cup itself. This is mounted directly to the jig with an insert that takes place of the ball joint. The ball joint cup goes here, gets locked in place, and it can't move once this is tightened down. Now, if you were building an upper control arm and you had the components to build this, what you would do is you would assemble the arm, you would assemble your pivot cups with the nuts on it, but you would not tighten it. You would leave it a gap for expansion. You would also leave the Zerk fittings out and you wouldn't put any grease in it yet. What you would do is you would mount your ball joint cup this cup here, would be mounted to the end, just like that. And depending on how your upper control arm mount is, you can build the arm out like this one, which comes out in a nice straight curve. This one kicks in a little bit sharper and it's a little bit longer. And it depends on how you want to build your upper control arm, but this is how they're measured. These I would put in a tube bender and I would bend them typically to clear the shock on one side and straight on the other to clear the upper control arm mount. So we'll take this component out and we'll talk about the measurement. Now this is an 11-degree stanchion here. How do I know it's 11 degrees? It's marked on the other side. What does that mean? That means if the ball joint is mounted at 0 and my control arm is mounted in here, this angle on the control arm is going to be 11 degrees. We'll grab our angle finder and we'll measure this degree. As you can see, measuring this one, it comes in at 11 degrees, which matches our actual angle stanchion. So we know that's an 11-degree control arm with a standard ball cup on the end. Now, this one is also an 11 degree. We'll put this in and we'll measure it as well. Now that we have that control arm mounted in here, this is going to be our 0 side. This is the side in which we mount our control arms in the Camry COT. The control arm plate is here and our jack bolt is in here. So this is the way it's going to go. Now this control arm says 1/2 inch forward left side. So let's flip it around again and take a look at it. Right here, as you can see on the jig, 1/2 inch forward. So here's our center. We're at the 1/2 inch mark. If we're on the left side and this is 0, and that is forward of that mark, that is a 1/2 inch forward. And as you can see, the markings that are stamped on here help you read it and figure out where it's at. Pretty simple stuff. That's how upper control arms are measured. Now, why is this arm at 11 degrees and this cup at 0? If this was mounted in our car and it was at rest, you would want the ball joint cup to be standing up straight. Reason being is it gives it the most articulation. Now, if you don't have a fancy jig, you can do this with some simple machine rules or even a square. Measure the length of your total control arm. This one comes out to 12 inches end to end the shaft. 6 inches is the center. When I square up my machine rules here, I measure it straight out. I can see that my ball joint right here is centered, so it says 0. I know the ball joint is centered and it's not offset. The main thing to look for is whether or not it's marked left or right. That way you'll know whether it's forward or backwards of center when you measure it. That's pretty simple. Now it says 8 inches. Now this is where a lot of people get messed up when it comes to measuring the 8 inches of a ball joint. Now I've seen many people say you measure it from the back, you measure it from the front, you measure it from the center. I've always gone from the center. The center is the articulation point of this shaft. It doesn't articulate off the front, it doesn't articulate off the back, it articulates off the center. So I always measure from the center of the shaft. This one is supposed to be 8 inches. Metal machine rule, center of the Zerk fitting, center of the shaft. It measures out to 8 inches right there. Pretty simple. Nothing hard about these things, nothing hard about measuring them. What throws people off from time to time is the markings that different teams put on them. I've seen some control arms from a team that has won championships where they just put a number on it. And that number might be 127.6 and it'll have a letter on the end of it. X, Y, Z, N, P. And those are their codes so that if somebody walks up to their car and looks at the control arm going through inspection, they don't know what's on it. They don't know the length. They don't know if they're using a short arm for caster gain or camber gain, drop arm. They have no idea what people are using because some teams put codes on here. So this is a simple way for you to measure it with 2 slide rules all on your own. Let's talk about adding a camber shim and adding negative camber to your car, which means the top of the wheel leans in. It's conducive to road racing. This is a 3/8 shim from CV. Drops right in, tighten up the bolts. You will check your camber setting and see where you're at, see if you're happy with that number. If you're not, you can loosen it up. If you need another degree or 2, slide it back. And you can add a multitude of different color shims in here to get what you want. You can go 1/8 inch, 3/16, 1/4 inch. Some of them are considered full control camber shims, which means the bolt comes out and the bolt bolts through here, holds it in, and it can't fall out unless your bolt comes out. Many of these shims have a peak at the top of them with a hole through them. As you can see, they come in different colors, different manufacturers, gold, blue, aluminum, red, it doesn't matter. They come in a multitude of colors and different shapes and sizes. But this hole typically is so that you can safety wire that control arm shim to the upper control arm itself or the mount. What many teams do when they don't have that, and the mount is a slip-in mount like this, and it doesn't have that, many of them will run a hose clamp through it and run it around the upper control arm and hold it in place. It's common practice among many teams to do that. We are back. Went inside and had a great lunch with the love of my life, and we're going to talk about lower control arms now. This is one of the big questions that I get because a lot of people, they buy used chassis or a bare chassis off the internet and they want to make it a roller. And they have no idea where to even begin to put lower control arms on something. I've seen some people that try buying like OEM Chevelle lower control arms and all this stuff because they think they're going to be the right width or the right offset. And they try putting rubber bushings in the stuff that should have monoballs in it, and it just doesn't work. It's not designed for that. Some of the stuff is based off OEM dimensions from back in the day. A lot of that hasn't carried forward, especially since about the mid-2000 and forward era going into the COT. In front of you, I've got 3 lower control arms laid out. This one is a Triad original that came on the COT. These are all marked as well. We're going to go over some of these markings. Now, this is an original to that car. This one has a 1-inch drop cup on it. It's a standard width. It's all marked on it, and we're going to go over that. This is an MWR control arm in the middle. As you can see, the monoball mounting surfaces are completely different. This on the end is a Gibbs road course arm, totally completely different as well. Now, I do have a set of these on that car because they're 3/4 of an inch wider than standard, which kicks the tire out at the bottom, adds more camber. A wider track width is more stable, and that's what we're going with on the front of our COT. But to break these down, we're going to break out the tape measure, and we're going to go over some simple measurements with these. Now, as I said, they're all different. Every manufacturer and every chassis manufacturer builds different control arms to suit their need. Now, the spread is where they mount to the chassis. That is where these monoballs mount to the lower portion of your chassis, depending on who made it, whether it's a Roush, a Laughlin, a Hendrick, a Hopkins, Joe Gibbs, Triad, TRD, you name it, there's 100 chassis out there. All the teams got into building their own chassis, and a lot of the stuff that teams build will not cross over to other manufacturers. So if you're trying to take a Turner lower control arm and you're trying to put it on a Roush car, it's not going to work. Your geometry is going to be messed up because they measure things from different points. Different measurements and different starting points lead to a different number in the end, and we'll talk about that. The first thing we're going to talk about is the overall spread going into the chassis. As you can see here, these are all different widths. This Triad one is exactly 15 inches. This is a Waltrip one, 14.5. Over here, a Gibbs, 15.25. So you can see that the width starting off is completely different between these 3 manufacturers. You have quite a different amount of parity there. Then we're going to talk about the width of the control arm. Now, you stand these up if you have a car and you buy them and you want to see if they are the equal length, pull the ball joints out of them and stand them up. See if they are the same width. As you can see, the Triad arm is a little bit longer and the ball joint cup is completely different and at a different angle because they travel different. If you look at this one, this has a standard spring cup in it. This one is plus 1 inch. It's kicked down 1 inch further for more travel and a different helix in it. If you look at these two, you can also see that the shock mount is completely different. This is a double shear shock mount mounted within the control arm. This is a single shear mounted to the outside. This one has multiple mounting tabs to move your sway bar in link depending on how the car pulls down and what the driver likes as far as handling. On the old original COT, there's only one place to hook up your sway bar, and that was it. As I said, these two, completely different generations. This is a Gen 6 MWR control arm. This is a Gen 5 early. It's even stamped, this one is stamped May, or no. Let's see, I've got the stamping on there. So this one is 3908. So that is March of 08 that this one is made. This one has an MWR number on it, but it doesn't have the date. And we'll look at some of these numbers as well. And what I'm talking about width, this is the road course control arm. I have a set of these on our Camry COT. This is the MWR arm. This is the road course arm. As you can see, 3/4 of an inch wider. That means where the ball joint is at, it's moved out 3/4 of an inch. This is an arm that we're going to use on that car. There's already 2 of them on there. This is an MWR. We're going to set that to the side and we'll compare it to the control arm that actually came off of our COT. We'll stand it up. As you can see, 3/4 of an inch wider. So this is preferable for road course racing. The reason being is that you can use a longer upper control arm and still gain the amount of camber that you want. A longer upper control arm prevents excessive camber gain when the car moves through travel. The longer the arm is, the slower the camber gain comes on. If you want to look into more things like moment centers, roll center, camber gain, and caster gain, there are 100 different videos and books out there talking about that terminology. In this video today, I'm just going to give you guys some of the basics so you know how to measure what you have and just make your car roll straight and turn left and right. Let's go to the table and we'll take a look at some other things that we have there. What you see here is my lower control arm table and jig. This table helps me to modify, measure, and build matching lower control arms for vintage road course applications. This table came from Hendrick Motorsports. I bought it from a friend of mine, Mr. Danny Earnhardt, who's no longer with us, and I built several and modified several sets of control arms using this table. What this does is it allows us to measure the ball joint center line from the center line axis of the monoballs to the ball joint itself. This also allows us to measure how far back from the center line of the table, the standard, which is this engraved line here, and there's a cross-section line here with a pivot point. What that allows us to do is it allows us to measure the center line of the pivot point of the monoballs out to the ball joint itself. It also allows us to measure how far off the center line the ball joint may be moved forward or backwards for caster gain or caster loss. This also adjusts wheelbase split to help a car turn left. This control arm here is marked CT2110-07. So it was made in November of 07. And here it says +1/2. Now measuring it on this gauge and where it reads out here is that it is +1/2 inch wide, which allows the left side of the car to be wider on a left turn and also give it more positive cast. So what that means is when you push this ball joint all the way back and you stand that caster up on that spindle, it will allow you to split it more. So this one stands up more, the one on the right side lays back, and it helps the car turn. It's called caster split. That is what the +1/2 can help in a non-road course application. In a road course application, +1/2 or 3/4 on each side helps to spread the ball joint and give you more camber. Pretty simple. Don't get caster and camber confused. I hear a lot of people that do it. I'm going to grab the camera and we're going to walk around this side and we're going to look at some of the numbers that are on everything. With this control arm, it's easy to see where it says COT 21 right here, and back here it says +1/2. If we go here and we read our gauge where the ball joint center line is, we can see that that is +1/2 inch exactly right where it needs to be. So that tells us that this control arm is 1/2 inch wider than stock. Now what we can do to replicate this, if we wanted to build another just like it, +1/2 inch wide for a road course application, is first thing we would do is flip it over to the other side, set it down, and we would take measurements here. So we're a +1/2, and this line here says that we are exactly on the standard, which is the center line. So the ball joint is not forward and it is not reverse on this car. So it's not offset forward and it's not pulled back. It's right on the center line where it should be. We have a standard ball joint offset +1/2 inch width on this control arm. So you can see the +1/2 inch right there. And that fits our control arm where it needs to be. So what we'll do is remove this. I would take another control arm, the right side, and we'll measure that real quick. Now that I have this lower control arm mounted up, I can see that the center line is correct. Raising it up, I can see the mark on the back here follows described on the table for standard. The arm itself is about 1/4 of an inch in difference. The other one was a +1/2, and this one is a +1/4. Although it's not marked on here that it's a +1/4, it says COT 22 standard +1C, which tells me it's got a 1-inch drop cup, but it doesn't say it's +1/4 inch wide. Pretty simple. Now when it comes to the markings on these tables, you can see that this is marked right side. This is our X axis, plus or minus. This, it shows you which way it goes, forward and backwards, and this is our Y minus going this direction. The table is marked for the standard location, so that is standard, and that is our center line that runs completely through the middle of the table. Come around to the left side, you can see our X and our Y axis is marked there. Now on the left side, there's standard, and there is -1/4. Why would you do -1/4? To get positive camber on the left side to help the car make a left turn. Other than the measurements that are already on this table for the standard width and the -1/4 for a left side, you can see our X and Y axis and where it's marked. Now, all of these holes that you see punched around on the table, they're there for a reason, and that reason is to insert the actual jig for a, let's see, what's this one say? Standard right front lower control arm for the chain. Let's see what we have here. Left front lower control arm link. So this one would go up here. Here we go. Left front lower control arm shock. So this one would mount over here, just like that. And when the control arm is flipped back over, or you have the correct control arm in here, you can mount your shock eye to the outside of the control arm, and then you can double shear your actual sway bar end link here. That's what these are for. You can take your tabs, put them on, bolt them through, and that will hold everything in place while you weld it to the control arm itself. And these come back off, and you just put them back inside the container, and you move on to building the next one. What we're going to talk about next is going to be some of the numbers on these control arms. Now let's talk about identifying some of these control arms and figuring out what some of the numbers mean. One of the easiest ones to go to is this one. This is the control arm that came off of the Shelmerdine car. It's marked COT 21, which might have been chassis 21 from what I'm thinking, 07. So this would have been an early build control arm, and it says +1/2 on it. I've already measured this one, so I already know that it's +1/2 inch wide. Those are some of the numbers you're gonna find, and they will be stamped in some of the most odd places. You'll find them inside the arm, you'll find them on the bottom, you'll find them on the shock shaft area. They will be all over the place. Now this is a Gibbs lower control arm. As you can see, it's got a tie down link on it, so they use a small tether to hold the control arm up for pit stops. This is for their shock, completely different than what you would see where this one, the entire bolt runs through the control arm. The actual shock shaft slides over it, and there's a retaining bolt on top of it. This entire insert is CNC machined. This one is too, but it goes through the entire control arm there. And on the inside, you can see where it's threaded. This one is threaded as well, and it just runs through. We're using this type on our COT Camry. Now it says 272 RC +3/4. I know this is 3/4 of an inch wider than standard, and we can see that really easy when we stand them up together. You can see how much wider that one is. Now this is an MWR control arm. This is a Gen 6 control arm. If you look at their Gen 6 cars that came from MWR, and BK Racing bought all the jigs and started reproducing this stuff, their Gen 6 stuff is different than everybody else. Their lower control arm mounting points are all CNC machined, and there's just enough space to put the monoball and a retaining clip in it. Versus these control arms, they use the wider mount with the monoball centered in the middle. It's quite a bit different. Will these work on this car? No, not at all. Why? Simply because of the mounting point and the way that the bottom of the lower control arm mounts to the chassis. This one, it may be hard to see, but right here, it's laser engraved MWR, lower control arm. And like I said, with some of them, teams just put numbers on them. You'd have to look in a book to figure out what this control arm is, as far as the width and what the drop is on it, or where the ball joint is placed. On this one as well, like I said, you'll see some of the shock mounting points are different. This one, the shock mounts inside of it and it's a double shear. There's a jet nut that drops in behind it. The bolt goes through it and it holds the entire shock in. Completely different thought of process from what you see with the Gibbs arm, where it slides on and just a retaining bolt holds it in place. Pretty interesting. Now let's talk about the monoball housings themselves and how they're mounted in the car. Typically, you will see an aluminum spacer like this, which holds it in place, and there is a slug that will determine how high or low this mounts in the car, and the width of these also determines how forward or backward in the car it may be. These come in different widths, they come in different colors, they come in different sizes. That's a 770 thousandths, that's 900 thousandths, this is 890 thousandths. And they just simply slide into the control arm monoball and you use a 1/2 inch bolt to mount them there. On the rear, it may have a pocket slug, which is a little bit different than just the front plate slug on the chassis. Now these may be flipped around. You may need a 770 in the front, you may need an 890 in the rear. It might be a 910 or 900, it might be a 1 inch. And it all depends on where your car is set up and how it's set up. My recommendation to everybody building a road course car is to center your control arm inside the plate mount, inside the chassis, left to right. I would center both of them exactly the same, and you may have to string your car to find that particular number. We're gonna go over to our COT. I'm gonna pull the wheel off. We're gonna put the front end on jack stands, and I'm gonna remove the spindle, and we're going to put a bare spindle on it so I can explain how caster and camber affect the spindle angle on the car and where those are adjusted. Let's do it now. It's a new day, guys, and I spent most of mine cutting a couple acres of grass. Last night I removed the front spindle assembly and the brake assembly from our COT Camry. Now I did that for a couple of reasons. I wanted you guys to see the bare bones assembly of how the control arm spindle and upper control arm go together and where the slugs are located and the actual names for them. A lot of times I get people that will message me with a bare chassis and say, I need a slug for this. They have no idea what it's called. They have no idea how to measure it, no idea what they actually need and where it's located at on the car. And we're going to talk about that. We're also going to talk about the effect of the slug in the alignment and with the caster setting of the car. We're going to talk about the steering arm, we're going to talk about the lower control arm and the upper control arm slug as well. How it allows both of those to move and how each setting adjusts everything. If you adjust the caster on this car, it's going to affect the toe. If you adjust the caster on this car, it's also going to affect the camber. All three work in unison. So if you make a change to one, you need to check the others to see how much of a change you have. You change the camber, it can change the toe. Change the lower control arm, it can affect the toe and the camber. It can also affect the caster. So if you start moving slugs around and start moving things around and suddenly your car's way out in left field, you should go back, restring the car, check the alignment, check all of your measurements, put an actual gauge on it with a bubble level to check the caster and camber setting on it and make sure it's right. Toe settings. Toe settings are another important thing. I can't give you the exact toe setting for your car or what you're comfortable with driving, but what I can tell you, an 1/8 inch out is a good way to start. Both wheels turned out, 1/8 inch total between the leading edge of the tire and the trailing edge. If you turn the toe in and the tires are facing each other inwards, they will chop. They're literally fighting each other and hopping over each other trying to move forward. They scrub off speed and they destroy tires pretty quick. Being towed out is kind of like what the camber does. When the tire is towed out, it wears the inside edge of the tire like excessive camber can. So what we're going to do is we're going to look at this. I'm going to show you, I'm going to take the camera, put it on the inside of the car where the engine would be, and I'm going to show you where the slugs are and what they're actually called. And then we're going to talk about moving the control arm up and down. I'll put the gauge on here so you can see the direct effect of moving a control arm without a slug in it. So let's take the camera, put it inside the engine bay, and we'll move the control arms around, and we'll talk about the slugs that are in there now. So here we are with the front suspension on our Camry. The camera is actually sitting on the sway bar tube, and as you can see, here's our steering box, our center link, our tie rod, our upper control arm and its mounting point. We have our lower control arm and both of its mounting points with lower slugs in it. This is considered a plate slug in the front. They come in various widths, length, thickness, and adjustments depending on the chassis manufacturer. You may find some that are longer than this, you may find some that are shorter, some that are wider, and some that are thicker. It all depends on what the chassis manufacturer and builder uses. Same thing goes for the rear. This is considered a pocket slug. Now this is an old school design. This has been around for ages. In some of the older cars, you will just see this slot cut in the chassis and two pieces of metal welded on each side of it. A lot of them didn't have a lot of adjustment other than the eccentric that was in it for caster adjustment. This is our upper control arm and control arm mount. In the rear, I simply have a slotted slug. That's what I use on the rear. I'll put a jam nut on the outside that will hold it in place. The hardware that's on here right now is just for mock-up and demonstration purposes. In the front, I would use a threaded slug for the upper control arm adjustment. Now in the front, you can get them that are simply with a hole in them like this that goes straight through, or you can get them that are threaded like this. I prefer the threaded method. That is a double lockdown point. So you can tighten the bolt within the control arm. You can also put a jam nut on the outside and lock it into place. That's not going to move fore and aft. With a washer and a lock nut on the rear with that slotted slug, that's not going to move either. For demonstration purposes, we'll put this washer and this coarse thread bolt back on here so that we can talk about the difference in caster adjustment there. On the lower end, there's another slug that goes into the pocket slug in the rear, and that one allows you to adjust camber in the bottom of the control arm as well. We'll move the camera to the outside and we'll talk about what effect the different slugs in the upper control arm and the lower control arm have on caster. Here is our physical demonstration model. I've removed the other spindle. This is just a mock-up that's on here, but it is a standard 10-inch height spindle. And what we're going to do is stick a magnetic angle finder on the spindle upright. And we're going to use this just for demonstration purposes only. This is just a physical demonstration. None of these numbers mean anything as far as the setup that I'm doing. And this spindle is not going to stay on the car, either is that spring. So this is nothing more than a mock-up and a demonstrator. Right now, with both control arms centered in the slugs, we're sitting right on 5 degrees of caster. Mind you, that's with a half back ball joint. It may be different on your car, and I guarantee you it will be. But I'm going to show you what some of these adjustments can do. Right now, we're at 5 degrees of positive caster. What does that mean? That means the top of the spindle is laid back 5 degrees, and it helps the car go straight. What we're going to do now is we're going to slide this upper control arm backwards and see how much more positive caster we can gain. That is all the way back, and we have gone to about 8 degrees of positive caster. Now mind you, this lower control arm here has not moved at all. It's still centered. So if we pull this one forward in the mount, that's going to push this bottom ball joint forward and give us more positive caster. Let's see where it goes from there. Grab the bottom, pull it forward, and right now we're sitting on 10 degrees of positive caster. That means the spindle's laid backwards. So when you let go of the steering wheel, the car, similar to your street car, wants to go straight down the track versus pull to the left. A lot of people ask me about that when they load or unload their car from a trailer. When they let go of the steering wheel, it pulls hard left going forward, or they try and back it out of the trailer, and if they don't hold on to it, the wheel goes hard left. It runs into the trailer and it tears stuff up. That's what positive caster can do. Let's see how much negative caster we can get out of it. Let's slide the lower control arm backwards. We are all the way in on the bottom and we're back to about 5 degrees. If we slide the upper control arm all the way forward, we are sitting on right about 3.5 to 4 degrees. Now this upper control arm is a 9.5 half back. Means from center of the ball joint to the center of the mounting surface, 9.5 inches wide, and the ball joint is 1/2 inch backwards on center. If this was a 9.5 0, that would more than likely be at 90 degrees and have 0 caster in it. That's just a physical explanation of what the slugs do and how you can move the control arms forward and backward. Whenever you make an adjustment to caster either on the lower control arm or the upper control arm slug, it will affect camber. You have to remember, moving this forward and backwards changes the rate in which it goes up and down. The angles change. Every single thing affects something else. The best thing to start out doing is figuring out how much camber you want in the car and set your toe. Get your toe as close to an 1/8 inch out as you can, and then start working on caster and go back through with your caster camber bubble gauge on the spindle and see how much it affects things until you get the number where you want. The upper control arm and camber can be adjusted by either shortening the control arm. Instead of going with a 9.5, you could go with an 8, or you can take shims out or add shims to move the center line of your upper control arm. It all depends on how much space you have between the upper control arm, the steering shaft, and your header on the back side. When it comes to bump steer, every car is also different. The amount of bump steer built into a car or the amount of bump steer that you can get out of a car depends on the insert that you put in the lower control arm steering arm and how much drop you have on it. This is a super speedway spindle and it only has 1/2 inch of drop on it. It's up pretty high. This super speedway arm works well on a car, especially with bump stops, because it's not going to move very far. You might get a 1/2 inch of travel out of it. On a conventional car that doesn't run bump stops and you have a lot of compression in it, this tie rod might come in contact with the lower edge of the frame rail here. Some cars you will see this is notched. That is a high travel car and it usually sits very low on the ground, sealed off. That's something else to look at. Here on our control arm is our shock mount. That's our lower shock mount. It's going to have an insert that goes on the end that helps hold the shock. It's conical and it allows the shock end to rotate and the shock will mount to the chassis up here. Now when I put the other spindle back on, it's also going to get a tether, it's also going to get brake lines, and it's also going to have the bump steer set on it as well. Like I said, all of this was just for a demonstration. Let's go over to the bench and we're going to look at a bunch of different examples of chassis slugs and inserts that you may need for your car. Let's talk about some front lower control arm inserts and spacers. These are the plate inserts that go on the front edge of the lower control arm. These are the control arm spacers, and these are the pocket inserts that go into the rear. Now, all of these have a different purpose. All of them are for a different manufacturer, a different chassis. As you can see, these are marked for Evernham. That's a Levitt. Here's an MWR Flame logo. That's a Hopkins, and this came off the TRD chassis that we have. Now, if you hold these two up, not only do you see there's a different number of holes, they're different spacing. Every manufacturer has a variety of these for adjustment of the front suspension. Another major factor is the thickness. As you can see, the Hopkins is much thicker, the TRD is much thinner. And when you hold them together, you've got about an 1/8 inch difference in the overall length of them as well. The most important thing to do, especially if you have a bare chassis and you're trying to find front suspension slugs, is to measure the recess length. There's going to be two measurements to measure. The recess length, that's 2 3/4 inch, as you can see there. And then you are going to measure the depth of the recess length. And this one is 3/8 inch thick. So you measure that, and then you know what you're looking for. Now, when it comes to the number of holes that are in this recess and the adjustment, that comes to final setup. But to get your car assembled and rolling, you can find many of these in different various widths, lengths, and heights at used parts houses. Now the control arm spacer, as you can see, these are all marked as well. 770, 890, 900, 910, and that's a 930. What does that mean? That's 930 thousandths from the actual taper here that goes into the monoball to the end of the spacer. We're just shy of an inch because that's 930 thousandths. These can be measured with a micrometer. Now, these vary in width also, and that's because you don't know how far forward or backward the control arm is going to sit, and you also don't know the width of the front pocket that these slugs bolt into and sandwich these inserts in. So when it's assembled, your monoball is going to be here and you're going to have an insert on each side. The thing is, you don't know the width of that lower control arm pocket until you measure it, figure out the width of your spacer and the monoball. Let's move these out of the way. We'll take all this and set it to the side. And when it comes to these pocket slugs, they too are just like the plate slug in the front. They come in various heights, various thickness, and various adjustments. As you can see, this is the thinner TRD Levitt style, and this is a Hopkins style. Turn them sideways and put them together, and it's easy to see how much thicker the recess is on the lower control arm mount for a Hopkins versus a Toyota. Now this will fit into a Hopkins chassis that has a 3-bolt design because it does not protrude further than this. Now, if I had a Toyota with a 2-slot design and this slug fit the overall diameter and this protrudes too far in, you can't use it. This is a Rowdy design, same thickness as the Toyota. I've got about 30 of these for my truck. Now the insert that goes into these adjusts the bolt back and forth, and that allows the control arm to move forward and back and adjust caster. All of these slug inserts are used in this type of pocket insert. It simply slides in and that centers the bolt over the hole and it doesn't allow it to move. Now a 0, if you find one of these with a 0 on it, 0 typically means that it is centered. It's not offset forward, it's not offset backwards, pretty simple. 3/8, this one says 3/8. Well, guess what? That means the center line of the hole is moved over 3/8 of an inch. Now, if you need one that needs to be 3/8 out, all you have to do is take it off and flip it over. You don't have to buy a different slug. Now these go in the front and the rear, and there are different various widths, and there are also different thickness as well. Now up until the late 90s, you saw an eccentric like this in the lower rear control arm mount of your car. Most race cars had this, and it had a bolt that went through the middle, and all they did was adjust the bolt, and the eccentric moved the bolt across the hole when you tightened it up. You could tighten it up here, and that could be your caster adjustment. You could roll it back, tighten it again, and this allowed for an even finer adjustment than what these had. Now the problem is with the slug insert, when you tighten the bolt down and you torque it, there's literally almost no way for this to fall out. Once this loosens up, no matter what, car going around the track, this can move back and forth as it loosens up. And this can allow for adjustment changes. That's why many teams went away from that, and you don't see it on anything anymore. You certainly don't see it on the next gen car. You don't see, I've never seen this on, I'd say, honestly, I've never seen this on a Toyota race truck, and they came into the series in 2004, but I've seen it on Dodge, Fords, and Roush chassis. Most of the stuff you see these days is an insert like this. As you can see here, we have center link inserts. This is not even scratching the surface on center link inserts. Some of the Red Bull stuff that's out there has special nuts to hold it to the center link and a special insert. This is just a bare bones example. They come in different lengths. You'll see some that are 3 inches high. You'll see some that are an inch thick. You'll see some that are 2 inches thick, depending on whether it's a Penske or a Red Bull. Red Bull had some crazy center links. RCR has some crazy stuff as well. And some of them will be super high. That's why you have things like this, which is a half slug. So this would go into the center link, and they would add another insert on top of it like that. That's how high some of these things are. You can also see some of those half inserts come in short links. You can see they come in aluminum. And this is simply for the center link, not the tie rod arm itself out on the steering arm. This is nothing more than a tie rod nut that goes on the end of the tie rod to lock it in place on the steering arm or the center link. If you get into Red Bull stuff, like I said, and RCR stuff, there's special nuts that go on them that are recessed and pretty long to go into the center link. But most of your steering arms use something like this to hold it in place. They're tapped for an actual tie rod end. They've got safety wire on them. This is a center link style that came off of an old Ronnie Hopkins center link, and there's a washer that goes on the back, and you can safety wire this to the actual center link itself. These 3 little bitty inserts down here, they make slugs for everything. I gotta tell you guys, they make them for everything. These are for a motor plate. That'll raise a motor or lower a motor 1/2 inch, depending on which way you turn it. This one's got an arrow on it for an 1/8, so it's an 1/8 down, and that's a 0. They come all in different sizes and different widths as well. Moving on, let's go to control arms. Here we have control arm inserts. So these are all of the slug inserts. This is probably, like I said, we're just scratching a surface on this. I have 3 full Vidmars that are nothing but chassis slugs and inserts. And I tell you, it's not even scratching the surface. Here we have some that are different heights. As you can see, all 3 of these are different heights. The holes are different. These are 1/2 inch, that's a 7/16. And you can see the difference in the hole size. You can also see the difference in the thickness of all 3 of these. Every single manufacturer thinks they can build a better mousetrap, and a lot of the times you'll see things. That's only an 1/8 inch difference on the mounting flange, but you can see it right there. Also, the thickness of the slug, quite a bit different as well. Every single manufacturer decided they were going to build something different as the sport evolved. These are simple Hopkins style. Now, this is a 0, straight drilled, bolt slides through, needs a jam nut on it. This is a Hopkins 1/16. As you can see, these are the same size, same offset, same thickness. And then we have a CV threaded insert. This is an upper control arm insert. I like to use these because this locks the hardware to the control arm and keeps it from moving. When it's mounted there, I put a washer and a lock nut on the outside. A mechanical lock nut works the best. Some other inserts, like I said, every team decides to build a better mousetrap. This is a Rowdy upper control arm insert. This is one that came off of a truck that I had. I had one time, I think 4 trucks that belonged to KBM, and I bought them all, and I used the parts off of them that I needed to build a good one. This insert, super thin, fits right into the upper control arm mount, uses a 7/16 bolt, works like a champ. Here's a Penske insert. Now, if you overlay them, they look exactly the same overall diameter, and the hole's a little bit offset. That's a 1/2 inch, and that's a 7/16. But as I said, every team tries to build a better mousetrap, and if you flip it over, Penske slug only works on Penske's control arm. Why? Instead of it being round on both ends, they decided, we're going to machine it square and we're going to round the corners. Once again, every team tries to build a better mousetrap. This is just an example of some of the stuff that you're going to run into when you're trying to make adjustments on a car or you're trying to build something from a bare chassis. Here we have upper control arm shims. As you can see, there's various colors, various thickness, but the center spacing on all of them is 6 inches. It's exactly the same all the way across all of them. An easy way to measure that is to go from the one end of the other to the next, and that'll give you the center 6 inches. Now, these are slide-in upper control arm shims made by CV. These right here, they just come in different colors and thicknesses. 1/16, 1/16, 3/8, 1/4 inch. That's a 1 inch from Gibbs, says JGR on it. These are positive locking and positive control upper camber shims. If you see, they're not slotted. They're still 6 inches on center. As you can see, 6 inches on center, but once you bolt this in, you have to completely remove the hardware to take it out. What teams typically do is they will have 2 or 3 of these stacked in a car, and they'll put a hose clamp or they will safety wire it to the upper control arm mount so they don't fall out. As you can see with these two, one's green, one's red, but these are for a 7/16 bolt-on upper control arm. You'll find this in some of the KBM stuff, you'll find this in some of the Penske stuff, and some of the older Red Bull stuff. The difference is, instead of it just dropping straight down onto the control arm, you have one bolt that drops in, you slide it back, and then you drop it down. They believe that was one way to keep this from completely falling out as well. But like I said, they come in different widths, 3/4, 1/4, 1/2 inch, 1 inch, 1 inch from petty. It doesn't matter, as long as you have the right hole diameter. These are 1/2 inch, those are 7/16, but they're all going to be on a 6 inch split. I've never come across a Cup car that was not on a 6 inch mounting center. Well guys, that's a wrap on this video, and I appreciate you taking the time to watch it. It means a lot to me. It's just me in front of the camera, behind the camera, and editing what you see on the screen today. That's why I don't try and get you to subscribe to another channel, buy some crappy shirt, sticker, or get a membership. It's just me, it's a hobby, and it's taken some time to do this because I've been super busy. The day job has taken me from California to Road Atlanta to the Coke 600 and 500 spots in between. So finally, I've gotten this thing finished, edited the way that I liked it, and I hope you guys understand it. It was never designed to be a setup video. Without having a person's car in front of you, you can't give them a setup. Anybody that goes online and looks at a photo of your car and says, yep, put this magic spring and this magic setup underneath it and it's gonna run great. It doesn't exist, and they can't do that without seeing it. They need to know things such as horsepower, wheelbase. A lot of these things are mitigating circumstances that people overlook 100 times, and you end up with a car that rides like a square wheel wagon on a Conestoga trail. Understanding spindle height, the numbers on control arms, steering arm length, those are important things that you need to know. Many of the messages I get from email and social media, they pertain to this stuff. Hey, what kind of spindle do I have? How do I measure the spindle pin inclination? How do I know how tall it is? Why does my car turn left every time I let go of the steering wheel? Caster and camber are very important parts of getting your car to roll straight, come in and out of the trailer straight. One of the things people ask me all the time is, hey, I've seen videos of your car, you almost never touch the steering wheel, rolling it in or out of the trailer, winching it in or out. Caster, camber, and toe setup on the front of the car are a very big thing. That's why you almost see me never have to touch it, because it goes where it's supposed to. When you let go of the wheel and it hooks hard left, more than likely your car has a caster split in it, which means there's positive caster on one side, negative on the other. That helps the car cut through the corner in the center of a turn, and it makes it handle in an oval track application. You don't need that on a road course application or to make a car turn left and right. You need equal caster, equal camber, and you need to set the toe so that the car is not scrubbing and the front wheels aren't hopping. It's very important. When it comes to that setup as well, you need to be honest to yourself and the person setting up your car when it comes to horsepower. A lot of people like to lie and say, I've got a 900 horsepower, whatever engine, or I've got 1,000 horsepower of this. The car behind me is going to get a phase 11 motor. It's a TRD engine, 752 horsepower, 609 foot-pounds of torque. It's not going to set the world on fire, but the way I drive it and the way I'm going to drive it, it will haul ass and carry momentum through the corners with a dry sump engine and a good transmission. I'm going to enjoy it. I appreciate it. I thank every one of you for watching. If you have more questions, comment below. Reach out to me on social media at stockcarsurplus, at stockcarsurplus@gmail.com if you have questions. I greatly appreciate all of you again and your patience to watch this video and wait for it to come out. Thank you.